working rule when x is equal to 0 is a singular point. So step first we shall compare the given differential equation to standard form d2y upon dx2 plus p dy by dx plus q y equal to 0. So this is the first step. Second step is that p and q are infinite when x is equal to 0. So we will check what is the value of p and q and confirm that x is equal to 0 is a singular point. Then taking solution of given differential equation means a series of the form y is equal to x to the power k sigma n is equal to 0 to infinity cn xn. This is nothing but n is equal to 0 to infinity cn xn plus k. So this is the second step. Third step is that we calculate y double dash. What is y dash? dy by dx and d2y by dx2. So we calculate y dash and y double dash and putting these value in given differential equation. Okay, given differential equation. Next step is that we will equate to 0. We will equate to 0 the coefficients of lowest powers of x. Coefficients of lowest powers of x. Okay. So we get a quadratic differential equation in terms of k. So we get a quadratic differential equation in terms of k. Suppose this is quadratic equation a k square plus b k plus c equal to 0. Okay. So this is very important equation. This is known as indicial equation. What is the name of this equation? This is known as indicial equation. Okay. This is indicial equation. Now, this equation have three category. Means quadratic equation in terms of k have two values because we have every equation of n degree has exactly n roots. So this equation have two roots, k is equal to alpha, k is equal to beta. Okay, so now we categorized this indicial equation in three category. So first category is that if two roots alpha and beta not equal, means alpha does not equal to beta, and second condition here their difference is not an integer, means alpha minus beta not belongs to set of integer, means their difference is not an integer. Okay. Second condition is that both roots are equal, means alpha is equal to beta. And third condition is that alpha does not equal to beta, but their difference is an integer, means alpha minus beta belongs to I. What is I? I is set of integers. Okay. So now we will explain one by one, means case first. This is case first. Alpha does not equal to beta and their difference does not belongs to I, means difference is not an integer. Second case, alpha equal to beta, means roots are equal. And third case, alpha does not equal to beta, but their difference is an integer. So this is case first, this is case second, and this is case third. Okay, so we shall start from here. Means when x is equal to 0 is a singular point, then these are steps, okay, which will follow. First step is that we compare given equation in standard form, means coefficient of d2 by upon dx2 is 1. Then we check the point x is equal to 0 is a singular point, okay, or ordinary point. So here p and q are infinite, either one infinite or both infinite, okay. Next step, when we checked this is a singular point, then we will take series of the form, this form, okay. Third step is that we calculate derivatives, means dy by dx and d2y by dx2, and then putting these derivatives in given differential equation, okay. Next step is we equate 0 coefficients of lowest powers of x, okay. In this case we get a quadratic equation in terms of k, means second degree equation in k. So k has two root, alpha and beta. So there are three cases arises. First is alpha does not equal to beta, but their difference does not belong to I, okay, means root are not equal and their difference is not an integer. Second, both roots are equal. Third case, roots not equal and their difference is an integer, okay. So we will explain one by one. So solve differential equation 4x d2y upon dx2 plus 2 dy by dx plus y equal to 0. This can also be written as 4xy double dash plus 2y dash plus y equal to 0 by series solution method, okay. So first we will write the given equation in standard form, okay, means coefficient of y double dash is 1. So first we write y double dash plus 2y dash, means on dividing by 4x, so 1 by 2x y dash plus 1 by 4x y equal to 0, okay. So this is a given differential equation. So both are equal, but our aim is to compare given differential equation to standard form. So first we divide coefficient of y double dash, okay. So this is a standard form. Here p is 1 upon 2x and q is 1 upon 4x, okay. So now when x is equal to 0, then p and q are infinite, means x is equal to singular point, x is equal to 0 is a singular point, okay. Now when x is equal to 0 is singular point, then suppose solution of given differential equation is y is equal to c n x to the power n plus k, n is equal to 0 to infinity, okay. In other words, you can write also this equal to xk sigma cn xcn, n is equal to 0 to infinity, okay. Now next step is that we calculate y dash and y double dash, okay. So this is very easy because we differentiate with respect to x, so because these are constants, for easy to solve, you can also write this is C0 x1 x for n equal to 0, C0 plus C1x plus C2x square, and we multiply x power k. Okay, so this is nothing but x की power k C0 plus C1x plus C2x square plus up to so on. Here plus Cn x n, and we multiply ck into each term of this bracket, so we get C0 xk plus C1 xk plus 1 plus C2 xk plus 2 plus Cn xk plus n plus up to so on. So I want to explain, because we calculate y dash and y double dash. So now this is very easy. We will use this type because this is very short. So now putting the value of y dash, y double dash in given differential equation. So substituting y dash, y double dash in given equation 1. Okay, so what is the equation? Y double dash means sigma Cn x n plus k, this is y, and y double dash means derivative of this thing double dash, and n is equal to 0 to infinity. Okay, now next step is plus 1 upon 2x y dash. So y dash is nothing but Cn x n plus k, this is y, and dash means this is dash. Okay, plus 1 upon 4x y, y is n is equal to 0 to 20, Cn x n plus k, this is y equal to 0. So next step is, this is differentiation of this function 2 times. Okay, so here Cn is constant. Okay, and sigma sign means there are infinite number of terms in sum. Okay, so here this will be n is equal to 0 to infinity n plus k minus 1 Cn x power n plus k minus 2, because when we differentiate first, so n plus k x to the power n plus k minus 1, and then again differentiate, so n plus k minus 1, and here minus 2. Okay, plus 1 by 2x, and here n is equal to 0 to infinity, differentiation only 1 times, so Cn n plus k x to the power n plus k minus 1. Okay, plus 1 upon 4x, here no any differentiation, means sigma Cn x n plus k n is equal to 0 to infinity equal to 0. So next step is only we solve, means on manipulation, means this is n plus k, so n plus k n plus k minus 1 Cn x to the power n plus k minus 2 n is equal to 0 to infinity, plus here 1 by x, means if we multiply in whole terms, so this will be 1 by 2 sigma n is equal to 0 to infinity n plus k Cn x to the power n plus k minus 2. Okay, and next term plus 1 by 4, this can also be written as sigma n is equal to 0 to infinity cn x to the power n plus k minus 1 is equal to 0. Okay, so now our aim is to collect same power of x. So here x to the power n plus k minus 2, x to the power n plus k minus 2, but here x to the power n plus k minus 1. Okay, so lowest degree of term means n plus k minus 2. So this can also be written as sigma. Here this is one terms greater than this term, means lowest degree term of x, there are two terms. Okay, so as we know before that step of calculating this method means first we equate 0 lowest degree term. Okay, so here one thing also I want to explain how we can write in terms of this coefficient. Okay, so we have sigma n is equal to 0 to infinity cn x n plus k minus 1. So when we get n plus k minus 2, if we put n is equal to n minus 1, okay, so this is equal to n is equal to 1 to infinity, means n is equal to n minus 1. This is infinite series. So cn minus 1 x to the power n plus k minus 2. Okay, so here we can write sigma n is equal to 0 to infinity n plus k minus 1 plus 1 by 2 n plus k cn into x to the power n plus k minus 2 plus, this is the term in the form of x to the power n plus k minus 2, means this is sigma n is equal to 1 to infinity cn minus 1 x to the power n plus k minus 2, and this is last term means 1 by 4. Okay, so this will be 1 by 4 equal to 0. Okay, so now for n is equal to 0, we can write k minus 1 plus k by 2. Okay, see 0 x to the power k minus 2 plus sigma n is equal to 1 to infinity n plus k minus 1 plus 1 by 2 n plus k cn x to the power n plus k minus 2 plus 1 by 4 sigma n is equal to 1 to infinity cn minus 1 x to the power n plus k minus 2 is equal to 0. Okay, so by taking n is equal to 0, this is first step, and then sigma n is equal to 1 to infinity, this. Okay, so now for initial equation, I know coefficient of lowest degree of x is 0. So now equating to 0 the lowest degree of x means x to the power k minus 2. Then we get initial equation. Okay, then we get an initial equation k k minus 1 plus ky2 equal to 0. ky2. So k minus 1 plus 1/2 equal to 0. Now 1/2 minus 1, k minus half equal to 0. So here the value of k is equal to 0 and 1/2, means these are alpha and beta. So I have discussed before, when roots are different and difference is not an integer, so here the type of root like alpha is equal to 0, beta is equal to 1/2, alpha not equal to beta, and alpha minus beta not belongs to I. Okay, so now I want to obtain next, means further constants like C1, C2, C3, all the constants. Okay, so for this we need the next coefficients of lowest degree of term systematically 0. So now to obtain the constants C i's, we equate the coefficients of x to the power n plus k minus 2 is equal to 0. Okay, so here it is clear that the coefficient of x to the power n plus k minus 2 is this thing, means n plus k, this thing and this. So n plus k n plus k minus half Cn plus 1/4 Cn minus 1 equal to 0. Okay, so this is the main equation to obtain the coefficients, means we can obtain very easily all constants by this equation. Okay, so now here Cn is equal to this will be right hand side, so minus Cn minus 1 upon 4 n plus k, then n plus k minus 1/2. So this is nothing but we can solve very easily. Cn minus 1, so 2n plus k minus 2 to cancel, so 2n plus k and 2n plus 2k minus 1. Okay, so this is Cn. Now case first. Case first means when k is equal to 0. In this case our Cn equal to minus Cn minus 1 upon 2n plus 0, here 2n minus 1. Okay, this is nothing but minus Cn minus 1 upon 2n minus 1. Okay, so now putting the value of n, means when n is equal to 1, so C1 is equal to minus C0 upon 2 into 1, so this equal to minus C0 upon factorial 2. Okay, n is equal to 2, implies C2 equal to minus C1 upon 2, means 2 to 4 into 3, 4 into 3. Also we have value of C1 from here, so minus plus, C0 upon 4 into 3 factorial 2. So this equal to C0 upon factorial 4. Okay, now for n is equal to 3, C3. C3 is equal to minus C2 upon 3 means 3 to 6 into 6 minus 1 5. So we have what is C2? C2 is nothing but C0 upon factorial 4. So this equal to minus C0 upon 6 5 factorial 4. So this equal to minus C0 upon factorial 6. Okay, so now substituting the values of these constants. Now substituting the values of C0, C1, C2 up to so on in given series y is equal to c to the power k C0 plus C1 x plus C2 x square plus this thing. Okay, so what is k? So k is 0, so y is equal to c to the power 0, x to the power k, x to the power 0 is equal to 1. So this is C0 minus here C1 is nothing but C0 upon factorial 2. So C0 upon factorial 2 plus C1 is C0 upon factorial 4. So C0 upon C1 is C0 upon factorial 2, here x. C2 is C0 upon factorial 4, x square. C3 minus C0 upon factorial 6, x cube plus to so on. So at least we will write 3 non-zero term. Okay, this is compulsory to write 3 term which is non-zero. Okay, so this equal to C0 1 minus x upon factorial 2 plus x square upon factorial 4 minus x cube upon factorial 6 plus up to so on. So this is solution for k is equal to 0. Okay, similarly case second means when k is equal to 1 by 2. So in this case we calculate the value of Cn minus 1. So we have Cn minus 1 is equal, Cn minus 1 is nothing but Cn. So now putting in this relation, okay, so here Cn is equal to minus Cn minus 1 upon 2n plus 1 into 2n. Okay, so for k is equal to half, this equal to minus Cn minus 1 upon 2n plus 1. Okay, now so we can solve similar method. So for n is equal to 1 implies C1 equal to, here n is equal to 1 means C0 upon 2 plus 1 3, 2 into 3. Okay, so this is minus C0 upon factorial 3. Now next n is equal to 2. So n is equal to 2 implies C2. So here C2 is equal to minus 2 minus 1 1. So C1 upon 4 and 5, 4 into 5. Also we have C1 is equal to minus C0 upon factorial 3. So minus plus C0 upon 4 5 factorial 3. So this is C0 upon factorial 5. Okay, so similarly for n is equal to 3, C3 means minus C2 upon 6 5, 6 and 3 into 6 plus 1 7. Okay, now what is C2? So C0 upon factorial 5. So minus C0 upon 6 7 factorial 5. So this equal to minus C0 upon factorial 7. Okay, so now substituting the values of C0, C1, C2 all the things in the series. Okay, so now again substituting these value in given power series, y is equal to x की power k c0 plus c1x plus c2x square plus, so what is k? So k is nothing but 1 by 2. So y is equal to x to the power 1 by 2 c0 plus what is c1? So c1 is nothing but c0 upon factorial 3. So minus c0 upon factorial 3x plus c2. c2 is c0 upon factorial 5 x square. What is c3? So minus c0 upon factorial 7 x cube up to so on. Okay, so now c0 is common, so we take common c0, so 1 minus x upon factorial 3 plus x square upon factorial 5 minus x cube upon factorial 7, okay, plus up to so on. So here y is equal to 1 by 2 c0, this thing. Okay, so now we obtain for k is equal to 0 and k is equal to half. So now complete solution. Now complete solution is y is equal to, first is c0 1 minus x upon factorial 2 plus x square upon factorial 4 minus x cube upon factorial 6. Okay, this is factorial 6. This is factorial 6. Okay, so here plus and plus for k is equal to 1 by 2. This is x to the power half c0 1 minus x upon factorial 3 plus x square upon factorial 5 minus to so on. So this is the solution. So you can write also, suppose c0 is 1 and here c0 is 1, so no problem, you can take, because this is constant. Okay, so you can also take here a and here b. Why? Because given differential equation of order 2, therefore solution contains two constant. Okay, so y is equal to a u plus b v. What is u? Where u is this thing, this is u. And what is v? Coefficient of c0, means x power half, and this thing, all the things v. So this is the solution and answer. Okay. Now next important problem is x square d2y upon dx2 plus x dy by dx plus x square minus n square y equal to 0. Okay, so this differential equation is known as Bessel's equation. Okay, here given that 2n is an integer. Okay, sorry, not non-integral. Okay, so it is very important that when we solve initial equation, so we get the values of quadratic equation. So when we get 2n, so then 2n is not an integer. Okay, so first we compare the given differential equation is d2y upon dx2 plus p dy by dx plus q y is equal to 0. So here our differential equation is d2y upon dx2 plus 1 upon x dy by dx plus 1 minus n square upon x square y equal to 0. Here also one thing is important, means in given equation also include n, because when we solve the differential equation by taking series, so we always take in the series contain term n. Okay, so now this is y double dash plus 1 upon x y dash plus 1 minus n square upon x square y is equal to 0. So this is for equation. So let the solution of 1 is y is equal to, as we know, y is equal to sigma. Here we have taken before solution n is equal to 0, but here in question already n exists, so we will not take here n. So another index, suppose m is equal to 0 to infinity. Okay, so here Cn is nothing but Cm x to the power m plus k. So this is important because in our given differential equation n is here, means n exists. So we will take for the series solution, our series contains m. Okay, so now this is 2. Now we calculate y dash, y double dash, and then we put the value of y double dash and y dash in 1. So we get now from 1 and 2 we have, it is very easy to explain, means y double dash. So this is m equal to 0 to infinity Cm x to the power m plus k double dash, okay, plus 1 upon x y dash, means m equal to 0 to infinity Cm x to the power m plus k dash, okay, plus 1 minus n square upon x square y is nothing but m is equal to 0 to infinity Cm x to the power m plus k is equal to 0. Okay, now we differentiate 2 times this term, so we get sigma m equal to 0 to infinity m plus k minus 1 Cm x की power m plus k minus 2, okay, plus 1 by x, we differentiate 1 times only, so this is m equal to 0 to infinity Cm m plus k x to the power m plus k minus 1, okay, plus here we have 2 terms, so first is 1 multiplied by this, so m equal to 0 to infinity Cm x to the power m plus k and minus n square upon x square m equal to 0 to infinity Cm x to the power m plus k is equal to 0. Okay, so now this is very easy. First, this is first term. I want to collect same power of terms, m is equal to 0 to infinity. So here m plus k minus 1 Cm x m plus k minus 2. This is very easy because only we will write here, no problem. So this is 1 upon x, so this x multiplied in an inner side, so we get plus m is equal to 0 to infinity Cm m plus k, and this should be x to the power m plus k minus 2, because here 1 upon x, so minus 2, okay, and here also minus 2, so here n square upon x square sigma m equal to 0 to infinity. So here we will take in with m plus k, so Cm x to the power m plus k minus 2, and only this term means m equal to 0 to infinity Cm x to the power m plus k is equal to 0. Okay, so now we collect same power of x, means x to the power m plus k minus 2 here, x to the power m plus k minus 2 here and here. So by collecting same power of x, so sigma m equal to 0 to infinity. Here Cm x power m plus k minus 2 is common, so m plus k minus 1, this is first term, plus m plus k second term, and this is minus n square. Okay, and here x to the power m plus k minus 2 into Cm. Now this is last term, means plus sigma m is equal to 0 to infinity Cm x power m plus k is equal to 0. So here we see that lowest degree term means m plus k, and here m plus k minus 2. So first we put m is equal to 0, so we get first term m is equal to 1, second term, and then third term we get m plus k. Okay, so this can also be written as sigma m is equal to 0 to infinity. Here m plus k is common, so m plus k minus 1 plus 1, so m plus k ka whole square minus n square. Okay, and this x to the power m plus k minus 2 into Cm. Okay, plus sigma m is equal to 0 to infinity Cm x to the power m plus k equal to 0. So now lowest degree term is m plus k minus 2, here m plus k. So first we expand by taking m is equal to 0, so first term by putting m is equal to 0, so k square minus n square C0 x to the power k minus 2 plus m is equal to 1, so second term k plus 1 square minus n square. Okay, this is second term, and x to the power k is m is equal to 1, so k minus 1 C1 plus this is m equal to 0 to okay, but here first term m is equal to 0, second term m is equal to 1, plus m is equal to 2, so we use sigma sign again, m is equal to 2, we will not write all the terms, so 2 to infinity m plus k square minus n square x to the power m plus k minus 2 into Cm. For this, okay, for this we have three term, first term, second term, and then infinite. For this m equal to 0 to infinity Cm x to the power m plus k is equal to 0. Okay, so now we need to calculate initial equation. Okay, so this can be written is very systematically, means k square minus n square C0 x to the power k minus 2 plus k plus 1 square minus n square x to the power C1 x to the power k minus 1 plus sigma m is equal to 2 to infinity m plus k whole square minus n square x to the power m plus k minus 2 into Cm plus last m equal to 0 to infinity Cm x to the power m plus k is equal to 0. So since we have sigma m is equal to 0 to infinity cm x to the power m plus k is equal to, because we need power of x is x power to the power m plus k minus 2, so we put m is equal to m minus 2. So here m is equal to 2 to infinity cm minus 2 x to the power m plus k minus 2. Okay, so now this can also be written as k square minus n square c0 x to the power k minus 2 plus k plus 1 square minus n square c1 x to the power k minus 1 plus, okay, in this place sigma m is equal to 2 to infinity m plus k square minus n square cm x to the power m plus k minus 2 and plus, again in this place we can write m equal to 2 to infinity cm minus 2 x to the power m plus k minus 2 equal to 0. Okay, so now we obtain the initial equation. So by putting 0 to lowest degree term of x, means coefficient of x to the power k minus 2. Okay, so we get here k square minus n square is equal to 0. So this is initial equation, okay, which is an initial equation. So as we know, what is the property of initial equation? This is second degree in k, so we get value of k. So here k is equal to k square is equal to n square, means k is equal to n and minus n. So in given question, difference, what is the difference? N minus minus plus, n minus minus plus, so 2n. According to question, this is not an integer. Okay, this is given, this has been given in question. So since this 2n is not an integer, so this is in case first, means both roots are different and their difference is not an integer. Okay, so now we will solve for further constants. So here again equating to 0, coefficient of x to the power k minus 1. Okay, so now equating the coefficients of x to the power k minus 1, means equating the coefficients of x to the power k minus 1. It means k plus 1 square minus n square c1 equal to 0. Since k is equal to n or minus n, for both the cases, this is n plus 1 square minus n square or minus n plus 1 square minus n square, so this is not equal to 0. So we have a into b equal to 0, either a equal to 0 or b equal to 0, but this is not equal to 0, therefore c1 equal to 0. Okay, so now I want to calculate c2, c3 up to so on. So now equating to 0, now equating to 0, coefficient of x to the power m plus k minus 2. So we get m plus k square minus n square cm plus Cm minus 2, okay, equal to 0. So this is the general value of constant, means Cm is equal to Cm minus 2. This is minus Cm minus 2, or we can write also n square minus m plus k square. Okay, so this is general value. So this is suppose 3. Okay, so now k is first when k is equal to n. So since we have Cm general value is equal to Cm minus 2 upon n square minus m plus k square. Okay, this is general value. So this is nothing but Cm is equal to Cm minus 2 upon k is equal to n, so n square minus m plus n square. Okay, so now since C1 is 0, so by putting m is equal to 2, so C2 is equal to C0 upon n square minus, here this is 2, so n plus 2 square. Okay, and similarly C3, so since C1 is 0, so C3 is equal to 0. Now C4 is 4 minus 2 C2 upon n square minus 4 plus k is nothing but n, 4 plus n square. Okay, so C4 is equal to 1 upon C2 upon this thing. Okay, and similarly C5 is equal to 0 since C3 is equal to 0. Okay, so by taking this constant, this is C2, so this is C2 is nothing but C0, so C0 upon n square minus n plus 2 square, and this is n square minus n plus 4 square. Okay, this is C4. Therefore we now putting these constants in our series, so we get y is equal to C0 x to the power k is equal to n, so x to the power n, and here C0 is common, so C0, first term is C0 1, and second term C1, so C1 is 0, third term C2, so C2 is 1 upon n square minus n plus 2 का square. Okay, so 1 plus, because plus 1 upon n square minus n plus 2 square, here x square, again C3, so C3 is 0, so C4 is nothing but this thing, so we have taken common C0, n square minus n plus 2 square into n square minus n plus 4 square. Okay, and x4 plus up to so on. Okay, so this is for k is equal to n. And similarly when we put k second, so suppose this is AU, k second means k is equal to minus n. So in this case we have Cm is equal to Cm minus 2 upon n square minus m minus n square. Okay, so in this case here k is equal to minus n, so this equal to c m minus 2 upon a square minus b square. So a minus b into a plus b, so this is cancelled. So this equal to c m minus 2 upon n minus m minus n minus 1 plus, so 2n minus m into m. Okay, so now putting m is equal to 0, so now constant c0 is already c0, c1 is 0, so c2 is equal to c0 upon 2n minus 2 into 2. c4 is equal to c2 upon here n square, so 2n minus 4 into 4 up to here. Also odd terms will 0 because c1 0, c3 0, c2 is equal to c0 upon 2 is common, so 2 into 2 4, here n minus 1. c4 is equal to c2 upon 2 is common, so 8 n minus 2, and here c2 is c0 upon n minus 1, so 4 into 8 n minus 1 n minus 2. Okay, so this is now c50 and again c6, so this can also be written as in this is c0 upon 4 minus n plus 1, c4 is equal to c0 upon 4 8 minus n plus 1 minus n plus 2. Okay, so by putting these value in upon our series solution, it means series, so we get, so by putting these constants in given series, y is equal to c0 x to the power minus n, so first term 1, second is 1 upon, because c0 is common, 4 minus n plus 1 x square plus 1 upon 4 8 minus n plus 1 minus n plus 2 x4 up to so on. Okay, so this is suppose 5 yani bv. So total solution is, hence solution is y is equal to au plus bv. Okay, so this is Bessel's solution of given equation. Okay,